Well, class. Okay, so we've been talking about waves, and let's say that we have a source of waves. This would be like a speaker producing sound, and say we have a wall here, and one of the things that waves do is carry energy. So if waves are directed at this wall, the question is, how much energy is going to strike this wall? And so we're going to define something called intensity as a way of measuring how much energy is carried by a wave. To start out, we'll come back to this example. Let's say we have a source of waves here. Now, if we're talking about sound, sound tends to spread in all directions, basically equally, unless it's directed. Like if we had some barriers here, they could reflect sound waves, so we'd kind of direct the waves towards the right. But, without guiding the waves, they'll spread out in all directions. Like if you drop a rock in a pond, the waves are going to move radially outwards. And, like a light bulb sends light waves in all directions. This is pretty typical behavior. And we're going to define, there's kind of two ways we can describe waves, because they're, fairly complicated things. Like here, we have a source of waves spreading energy out in all directions. And so the two main ways, one of them is a ray. So let's say there's a source of waves here, and then say there's an observer here. We can draw a line from the source to the observer. And, just consider like a wave travels directly from the source to an observer. This is called a ray. And if we plot the wave, you can imagine a wave on a string. Or if we're dealing with a sound waves, we can look at pressure differences, which look like, actually let me come back to that in a moment. We're going to consider a simple wave that looks like this. It's described by sine waves. Now, real sound waves typically don't look anything like this. We can record sound waves with something called an oscilloscope. That's one way to do it anyways. Like if you just look at like a conversation or like a real sound, it's not going to look anything like this. This is a type of sound wave that would be carried by something like a tuning fork. So like a tuning fork is designed to oscillate at a particular frequency. So you have your tuning fork, it looks something like this, and you strike it, and these metal bars just move back and forth. And so like when the bar is moving this way, it's compressing the air. When it's moving the other way, it's creating a partial vacuum behind it. So you get these like high and low pressure regions that are moving away from the fork. And it's designed so that these, I'm not sure what you call the little parts of the fork, but they move at a pretty constant frequency. And so they would create a wave that looks like this. Now, a real sound wave would be something much more complicated in general. But we tend to represent waves as sine waves for a reason. And this is definitely not something we're going to talk about in this class. But let's say we had like an actual wave. It might look something like this. Some complicated shape. What's interesting is that we can break this complicated shape into a sum of simple sine waves of different frequencies. So you could have like sine of x, which would look like this. Say it looks like this. And then if you have sine of 2x, it would look, something like that. Sine of 3x, you get a shorter wave. And the thing is, if you add up these waves, you can get different shapes. And so adding is kind of a straightforward process in principle. To add two waves, you just add the amplitudes. We'll talk more about that later. But what's interesting is if you have something like this, you can actually figure out the components of this wave in terms of sine waves of different frequencies. It's a fairly complicated process. It's called Fourier analysis. Definitely beyond what we're going to be doing in this class. But kind of getting off subject here. But yeah, I'm using an example of sound, and this is not a typical sound wave. But this is kind of the foundation for real sound waves. We look at sines and cosines. So regardless of the actual shape of the wave, you know, we always deal with these simple sine and cosine waves. Okay. Now let's look at, we can mark areas where we're at a maximum amplitude. Like as we just move from this away from the source, you know, we have the maximum amplitude. We can mark those areas on a ray. And this is just one ray, representing a single wave going from the source to the observer. But again, you can have a ray going in a different direction, and if you mark off in a different direction, I won't draw the wave itself, but it's going to have these, it's symmetrical. So the peaks of these, of each individual wave is going to be the same distance from the source. They're going to be the same distance. And so we can, you know, if we draw rays going out in all directions and connected those points where the amplitude was at a maximum, we would get something that looked like this. And these regions where the amplitude is at a maximum, these are called wave fronts. So a wave front is a region where the amplitude of the wave is at a maximum. Now, this picture here, this is what the wavefront would look like at one moment in time. Just like this would be the wave at a moment of time, but the wave is moving away from the source. And so like all these peaks are moving away as well. So if you're able to visualize this, you know, as time goes on, these wavefronts are spreading out and new ones are being created. And so again, this whole pattern is expanding and moving outwards. And new ones are created every time we go through one cycle. And the distance from one wavefront to the next is a wavelength, the wavelength. Now, one more thing I'll say about this picture. It looks like these wavefronts are circular. However, they're not actually circular. They are spherical shells, because waves spread in all directions, including out of the board. And but we can't draw that, so we're just looking at a cross-section of a sphere, which is a circle. But yeah, they're actually spherical, and it's important to keep that in mind, because something that we're going to come across later, we need to know the surface area of a sphere. So if you look at the picture and you want to think at a given radius, what's the surface area? It's very tempting to say pi r squared, because that would be the area of that circle. But we have to remember this is it's existing in three-dimensional space. So the surface area of a sphere is 4 pi r squared. And that's on the equation sheet. You don't need to memorize that. Okay. So yeah, two ways to represent waves. One is with a ray, and the other is with wavefronts. Now, we notice, however, that the wavefront is like perpendicular to the ray. Now, sources of waves usually produce waves that are spherical. You know, if things spread out in all directions equally, the wavefronts are going to be spherical. So these are called spherical waves. However, what if you're very far from a spherical wave? What if we have an observer over here looking at this source? These wave fronts are going to be, very large spherical waves. And if you're just, this person's only going to see a very small portion of this wave, and if you're far enough away, the curvature here is going to be negligible. And so at a far distance from a source, if we plot some of these wave fronts, we can basically say that these are plane waves here. Because we're just seeing a small portion of these waves. Just like if you go outside, we know that the Earth is roughly spherical, but we can say the ground is typically flat. It's very difficult to detect the curvature of the Earth visually, but the curvature is insignificant. Irregularities in the ground can be significant, but you're not going to really notice the curvature of the Earth over a small area. Just like the same, if you're far away from the source, we can ignore the curvature, and then we have plane waves. Okay, and again, spherical waves are nice, plane waves are nice. If you're somewhere in the middle where there's some curvature, well, that would just be like an arc of a spherical wave, but plane waves are nicer to deal with. But let's get back to this example. Say we have a source of waves, could be anything like sound or light or whatever, and it's sending waves to this, let's say it's far away, so that the wave fronts that are hitting it are basically flat by the time they get there. And how much energy is being directed towards, here I'll make this, let's make these wave fronts big enough to fully hit it. So we have this barrier, so it's like how much energy is going to be absorbed, or how much energy is incident upon this barrier? That's an important question. And what factors are going to determine this? One thing is the area of the barrier. Now, there's another factor that I don't really want to deal with, but let me erase this barrier for a moment, and I'm going to draw a barrier with the same area. However, it's going to be at an angle. And again, there will be less energy hitting this barrier than the one that's perpendicular to the wave fronts. And so the orientation can matter as well. But we're not going to really worry about that. I mean, it's easy enough to deal with. If you have a source of plane waves striking a barrier, if they hit it at an angle, you can see the part that's blocked by the barrier. We would just say this is the effective area. Just a part that's actually blocked. Part of the wave fronts that are actually being blocked by the barrier. So we can just throw that into the area. Say if the orientation is a factor, we'll just take that into account and define the area this way. Okay, so the area of the barrier is a factor. Time is also a factor. A very practical example of this, let's say this is a solar panel. And orientation would definitely matter here. You want if you have a solar panel, you want it to be, you look at the sun coming down and hitting your panel, you want the normal vector, or like a perpendicular line to your surface. We can draw a normal line, which is perpendicular to the surface. We want that to be perpendicular to the wavefront so we catch as much of the light as possible. And again, if you have a solar panel, the more time you leave it out in the sun, the more energy you're going to absorb. So area and time are factors. And the wave itself again, go back to the solar panel. If you, like if it's a cloudy day and there's not much sunlight, you're not going to get much out of your solar panel. Where if it's a very bright sunny day, you get more energy. And so the wave itself is a factor as well. So the total energy that's going to strike the surface depends on basically these three things. Now, we want to isolate the properties of the wave itself. So we're going to find something called intensity. Now, I'll just check the notes. In the notes, I use I for intensity. Sometimes the intensity is written with the variable S, but, I or S, either way. So the intensity, we're going to define this as the power over the area. Oh, sorry. Just power over the area. So basically, we could say the energy delivered. Now, the energy depends on the area and time. So if we divide by the area and the time, then we're removing those. And so the intensity is just a property of the wave itself. And energy over time is power. So we can say intensity is power over the area. And that's how we define it. And again, that gives us a something that only depends on the wave itself. So intensity is a property of the wave, not what the wave is actually hitting. So it's a very important property of waves. The units are watts per meter squared. Let's write this down. Intensity is power over area. Measured in watts per meter squared. Okay, now a very special case is the spherical waves. So if you have spherical waves, the area, remember we have to consider a spherical shell, the area would be 4 pi r squared. And so here we have the inverse square law. The relation between the intensity and the distance from the source, that's described by an inverse square law. Say we have a constant power. So if you go twice as far away from the source, the intensity goes down by a factor of 4. And again, that's just generally a property of spherically symmetric sources, like gravity, inverse square law. Twice as far away, the intensity goes down by a factor of 4, or in the case of gravity, the force. If you're 3 times as far away, the intensity would go down by a factor of 3 squared, or 9. All right. Now, the most important example of this is sound waves. And I think I want to do this in 2 pieces. So I'm going to stop this one a little bit short because when we talk about sound waves, it's interesting, the intensity of the sounds that you hear can vary enormously. I mean, it's amazing the range of intensities that our ears can detect. And so we're going to design a scale to take this huge range of intensities and kind of bring it down to scale. And the problem is that this scale we're going to define, it's called the decibel system, that involves logarithms. And so I think what I'm going to do is I'm going to record a separate video just on logarithms, because I know you've all seen them before, you've had the prerequisites for this course. However, it's one of those things that you probably just saw once, and I've learned that when you're exposed to something once and you don't use it often, there's a good chance that at least some of you will not know everything you need to know about logarithms. If you do, you can skip the next video. So I'm going to make a separate video just on logarithms, and then we'll go back and talking about the intensity of sound waves. So that'll be it for this one.